Now we have discussed about the subject engineering thermodynamics. Topic is Carnot cycle. Myself, I am Java Singh, assistant professor, Department of Mechanical Engineering. Now we have discussed about the Carnot cycle. A Carnot cycle is defined as an ideal reversible closed thermodynamic cycle. So once again, the Carnot cycle is defined as an ideal reversible closed thermodynamic cycle. 4 successive operations are involved. First one, isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Once again, I will repeat again. That is very important. Isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So that is the four excessive operations. The expansions and compressions of the substance can be done up to the desired point and back to the initial state. The expansion and compression of the substance can be done up to the desired point and back to the initial state. During this operation, the expansion and compression of the substance can be done up to desired point and back to the initial state. Next, we go see about the thermal expansions. Heat is transferred reversibly from hot temperature reservoir at constant temperature to the gas at temperature less than TH to allow heat transfer to the gas without practically change the gas's temperature. So the isothermal additions are abstractions. During this step, the gas is thermally in constant with the hot temperature reservoir, while thermally they isolated from the cold temperature reservoir, and the gas is allowed to expand, doing work on the surrounding by gas, pushing up the piston. Stage 1, the figure will be there. So although the pressure drops from point 1 to point 2, the temperature of the gas does not change during the process. Temperature of the process during the process. Next, we have the process because the heat transfer from the hot temperature reservoir to the gas is exactly used to do work on the surrounding by the gas. So no gas internal energy changes. So see the diagram, that is a cold reservoir and hot reservoir, that is there the internal expansion is produced. Next, we have discussed about the isentropic. So isentropic, the reversible adiabatic expansion of the gas, that is isentropic work output. For this step, the gas is the engine is thermally insulated from both an hot and cold reservoir. Thus, they neither gain or lose heat. An adiabatic process. The gas continues to expand with reduction of its pressure, doing work on the surrounding. Raising the piston, the stage 2 figure, they write the losing an amount of internal energy equal to the work done. The gas expansions without heat input causes the gas to cool to the cold temperature by losing its internal energy. It is the infinite higher than the cold reservoir temperature, that is TC. The entropy remains unchanged as no heat Q transfer Q is equal to 0 between the system, that is gas, and its surrounded. So and the isentropic process, the meaning no entropy changes in the process. So an isentropic process meaning no entropy change in the process. Next, isothermal compression. Heat transfer reversibly to low temperature, the reservoir at constant temperature. In this step, the gas in the engine is in thermal content with the cold reservoir at temperature C. While the thermally isolated from the hot temperature reservoir and the gas temperature is higher than its temperature. To allow heat transfer from the gas to cold reservoir without practically changing the gas temperature, the surrounding to work on the gas, pushing the piston down. Stage 3, the figure right, an amount of energy and to by gas from his work actually transfer as a heat energy QC less than 0, the negative as the leaving from the system according to the universal conversion in thermodynamics to the cold reservoir, and entropy decreases due to compression. Next, isentropic compression. Once again, the gas in the engine thermally insulated from the hot and cold reservoir, and the engine is assumed to be frictionless and the process is slow enough, hence the reversible. During this step, the surrounding to work on the gas, pushing the piston down further. Stage 4, the figure right, the increases its internal energy, compressing it and causing its temperature to rise back to the temperature less than TH due slowly to work added to the system. But the entropy remains unchanged at its point, the gas in the same state. So you can see this the graph, that is the PV diagram that will be mentioned the temperature changes on based on PV. So the P will be mentioned on the y-axis, V will be mentioned the x-axis, that is the PV process. The P represented the pressure, volume represented the volume. The temperature will be changed on the process, the line will be mentioned, the chart. Thank you.